and hope everybody have a enjoyable Labor Day weekend. So we now start the second talk of this fourth semester. Now is speaker today is really a great pleasure to have Yacine Tani, and Yacine got his PhD from, I'll say, in 2006, and then after that he went to Seattle INT for 2 years as postdoc, and then University of Santiago from 10 to 11, and then he went back to France in Saclay between 11 and 2014, and I think since 2015 or 14, he's joined Brookhaven Lab, the theory group. So he will give us a talk about anomalous diffusion in QCD matter today. So go ahead, please.
Yeah, thank you, Xinyan. It's really a pleasure to be here and give this talk. Thanks for the invitation. Let me first.
Maybe you can share.
Yes, share my screen.
Yes.
Let's see how this works. Preview. Okay. So yeah. I guess you can see.
Yes, we can see that.
Full screen now. All right.
Very good.
Do you see my cursor?
Yeah.
I think I will be using it quite a lot. Okay, so again, thanks for the invitation. So I will talk about some recent work that I've been doing with Paul Kokal, who joined us as a postdoc at BNL last year. So this work is not yet published, but it will appear soon, hopefully. So the problem we tackled, which I'd like to discuss today, is related to quantum corrections to transverse momentum broadening, which manifests itself in a variety of processes that we study in QCD. So the title is Anomalous Diffusion in QCD Matter, which is basically just saying that quantum corrections will lead to this type of anomalous transport when we study transverse momentum broadening. So let me start with some generalities about anomalous diffusions, just to set the stage. So the really basic things. So we are all familiar with Brownian motion. I mean, this is kind of textbook thing that we learn when we start learning physics and statistical physics in general. So we know that any stochastic diffusive process tend to have this mean square displacement that scales linearly with time. This is the standard anomalous diffusion we're familiar with. There are other processes that exhibit anomalous diffusion. What we mean by that is that there's departure from this linear law here of this mean square displacement. So basically, when this exponent alpha is different from 1, which would correspond to standard Brownian motion, then we would call it anomalous diffusion. So there are two types, as you can see. You would have when alpha, the exponent is smaller than 1, this would be referred to as subdiffusion. So the diffusion somehow is cramped, and it doesn't really explore very much as fast as the normal diffusion, the space. There's another type of diffusion which is called the superdiffusion, and it does exactly the opposite, which is leading to a very rapid exploration of the coordinate space and leads to very rapid diffusion. And these different anomalous diffusion, it's not only about having different exponents. This leads to also qualitative differences in how the diffusion process takes place. So it's just kind of to set the stage, as I said, and just to give you here small flavor of the super diffusion walk, which is the Levy, called the Levy walk, as compared to the normal diffusion. So as you can see here, normal diffusion, you will have like typically very small steps that will turn, will take the particle to distances which are controlled by the mean square displacements, and typically doesn't the area explored by the particle doesn't really extend very fast with time. On the other hand, in a super diffusion case, in fact, the mean square displacement is not defined the same way. So moments of the probability distribution are not well defined. And in fact, what happens is that you would have arbitrarily large step lengths. And this leads to, as I said, arbitrarily large exploration of the space you can see here. So, and this is driven by a power law distribution that describes those very long steps that can take the particle, while it can diffuse a little bit here. As you can see, there's normal diffusion here. And then from time to time, we have rare events that we take the particle to another area, and then it starts diffusing again. That's a typical event. It will diffuse a little bit. And then from time to time, it again jumps. Then you see those jumps here that that are characteristic of a Levy flight. And just as a teaser, this is exactly what we're going to see, what we're going to experience when studying quantum corrections to QCD in terms of momentum broadening QCD. So this anomalous diffusion is quite normal, in fact, and rather common in nature. I think the first occurrence of this phenomenon was linked to Richardson, who was studying classical turbulence, so turbulence in the atmosphere, and he realized that the size of admixtures of clouds was increasing according to an anomalous scaling, which was not linear as standard diffusion. So it was increasing like t to the power 2/3. And they interpret, back then it was interpreted as being an anomalous diffusion. But in fact, later on, Kolmogorov provided his famous turbulence law of 2/3 explanation based on self-similarities and local breakup of eddies. So you see, so this is a rather general topic that touch upon many physical processes. And it appears, as you can see here, in biological systems, in homogeneous media also, molecular chemistry, optical lattice, and polymer transport theory, and many more, many more. So you can see this type of anomalous diffusion in many contexts. So here we will be interested in QCD and in particular transverse momentum broadening in QCD matter. So what we mean by transverse momentum broadening is if you shoot a particle, a parton, a quark or a gluon, a very energetic parton, which you would produce in high energy collisions and colliders. You can think of it as a jet. Would go through QCD matter. It's either the quark-gluon plasma formed in heavy ion collisions or a nucleus in electron nucleus collisions. And this jet or this high energy parton would go through that matter and would suffer random kicks. And those random kicks would, although the momentum transfer during those kicks would be much smaller than the energy of the propagating parton, it will still have an effect on broadening its transverse momentum with respect to the direction of motion. So if you would project on a transverse plane transverse to the direction of motion, you would see this type of random walk in the transverse momentum plane. And that's exactly what we're going to study. So how is this random walk occur on the KT space in QCD? All right, so this is a transverse momentum broadening appears in various of processes, and it's quite important in the study of nuclear matter, whether it's hot nuclear matter or cold nuclear matter. So maybe used to probe the quark-gluon plasma in heavy ion collisions. So there are certain observables that allow us to, that are very sensitive to transverse momentum broadening and can be used to probe the QGP. Such an observable would be a dijet azimuthal decorrelation. We would produce two back-to-back jets in a heavy ion collision. Those two jets would go through a QGP and suffer multiple scatterings, which would broaden their transverse momentum. In addition, of course, to standard gluon Bremsstrahlung that would also be could also be responsible for momentum broadening. These are two different effects. One is vacuum physics. The other one would be due to medium interactions here. And by measuring the transverse momentum of the final jets, or the imbalance, the azimuthal imbalance, this would tell us this will tell us about the properties of the typical transverse momentum scale of the plasma. And you can see it here in this calculation, where the distribution of the azimuthal angle between the dijet here is broadened, slightly broadened in the case of nucleus-nucleus collisions, as when compared to the case of PP, which also, as I said, exhibits some broadening due to Gluon-Bremsstrahlung and Sudakov effects, and the difference would be related to momentum broadening in the plasma. So this is recent work. There's also an interest in studying those effects to probe the rare events in the tail of the distribution here that may allow us to probe the so-called Rutherford scattering, to know a little bit more about the nature of the scatters inside the medium, whether they are point-like scatters or not. So this is very, as I said, these are different ways of seeing looking at the same problem, trying to probe the plasma, studying dijet events. Momentum broadening is also encountered in the study of cold nuclear matter, electron nucleus, studying some inclusive DIS, or forward dijet or dihadron production. For instance, in the context of small x physics, you see here the dijet, the dihadron here, azimuthal distribution in PP, where you see this back-to-back correlation, peaks, two peaks here, as compared to the in DA, deuterium gold collisions, where the wayside peak is suppressed due to, in fact, multiple scatterings in the final state. And this observable was also used as somehow smoking gun of saturation physics. And of course, dijet event that was also recently investigated to probe cold nuclear matter in electron nucleus collision. So this is a really somehow a very hot topic, and very difficult as it involves a variety of convolved processes altogether that need to deconvolve to understand the physics and probe the nuclear matter. So, as I said, this is a quite important element to understand momentum broadening if we want to access and learn about QCD properties, transfer properties, whether it's hot or cold QCD matter. So the probability distribution for a high energy particle to acquire transverse momentum KT after a certain time t, plasma obeys a Fokker-Planck equation. So of course, this is not valid everywhere in terms of space, but a typical event, this is how we would describe it. It's a standard diffusion. So you would have a diffusion coefficient called Q hat, which encodes the plasma properties, and the diffusion just proceeds as in a normal diffusion, and a typical transverse momentum squared would just grow linearly. So that's the standard picture. That's a leading order picture. That's what I wanted to stress here. So the question is, how does this change, or whether it changes at all, when quantum corrections are accounted for? And whether quantum corrections are important. Of course, we expect quantum corrections to be suppressed by powers of the coupling constant. So are they going to be enhanced by phase space factors, where they will change the picture? Well, we know that this is quite somehow to be expected. You know that in the study of proton structure, quantum corrections are critical to our understanding of the physics. We have naive part model, which provides, somehow a qualitative picture of the proton back in the 70s, but it was quite inaccurate. It didn't account for confinement. It didn't account for a lot of processes. But we know that quantum corrections are really mandatory if we want to understand better the structure of the proton. As you can see, this the account for them would lead to a variety of elements like the emergence of an anomalous dimension, the parton distributions, running of the coupling that somehow connects the weak coupling regime to the strong coupling regime, the appearance of the gluon degrees of freedoms, confinement, and of course, this leads to a better understanding of the spin decomposition of the proton. So as I said, in this cartoon here, you can see that the picture is a lot more complicated when accounted for the quantum corrections. So we may expect the same to happen if we study momentum broadening in the context of heavy ion collisions, for instance. So maybe a few words on the leading order picture. So in the independent multiple scattering approximation, where we assume that the mean free path is much larger than the medium correlation length, which is given by the inverse Debye mass, for instance, in a thermal plasma, or the size of nucleons in a nucleus. If this is much smaller than the mean free path, which is again much smaller than the length of the medium, if we have this large separation of scales, then we can treat multiple scatterings as independent. And then we can use just a standard master equation to describe to resum multiple scatterings. And then solving this master equation would allow us to compute this transverse momentum probability distribution. The rate at leading order would be simply given by the 222 matrix element, which goes like 1 over qt to the fourth qt being the momentum transfer in the T channel here. So this is just a 222 process in the T channel where the transverse momentum here is qt. And of course, we should expect this divergence, this infrared divergence, to be screened by the Debye mass when qt is of the order of Debye mass. All right, so this is the leading order picture. So what does it look like after solving the equation? Well, we have two regimes. The first regime is, as I mentioned before, when KT is a typical KT, relatively small KTs, we have standard diffusion, and standard diffusion is described by the transport coefficient Q hat, and a typical transverse momentum that describes the diffusion would be Q hat times the length of the medium. So Q hat L. This is a typical transverse momentum, and the distribution would behave roughly like a Gaussian. So this is the Gaussian peak here. Then, of course, this description would fail at large KT, because at large KT we'll have those rare events that have a power law tail, which is just a typical Coulomb tail that I showed before. This is the elementary process, this collision rate that goes like 1 over KT to the 4 that needs to be accounted for, and the description would be given by this power law here. All right, so just a digression here. These two regimes, for the moment, this is just qualitative. We still need to figure out what goes into Q hat. So when computing the diffusion coefficient here, we realize that because of the fact that the elastic cross section goes like 1 over qt to the 4th times qt squared, integrating over this, we would get a logarithmic UV divergence, which needs to be cut off at some UV scale here, Q max, which at this stage is yet to be specified. But this can be done analytically. And in fact, the scale, by simply taking the Coulomb law, going to coordinate space, which is somehow more convenient, taking the Fourier transform, the equation can be the Fokker-Planck equation, the master equation, rate equation can be solved, and it leads to this exponentiation here with Q hat in coordinate space given by simply some prefactor, some constant, which is proportional to the density of scattering centers times the Coulomb logarithm. And then by splitting the Coulomb logarithm into two pieces, one introducing some kind of factorization scale, Q squared, which will be specified soon. By just splitting, this is a trivial identity. You get a large logarithm. This Q squared is when we assume to be much larger than the infrared scale mu squared, which is typically the Debye mass, plus a log of 1 over x perp, which is the size of the dipole here, which is the conjugate to KT. So assuming that Q squared is of the order, or which is a typical value for the dipole size, then this log can be treated as a perturbation. This large logarithm here would be the leading term. So of course, if this is a constant, you look at here, this Q hat is constant, then you get Gaussian and you can integrate. Then you get a Gaussian, you get back this Gaussian here, right? And then this second log, which encodes a non-trivial dependence on x perp, can be treated as a perturbation and solved analytically. And then in doing so, we would fix this Q squared, which is in fact related to this to the UV scale here, as being this kind of saturation scale QS squared, saturation in analogy with saturation physics, and this will become more transparent later. And this QS is calculated by solving this implicit or transcendental equation. As you can see, QS squared has to be equal to the this prefactor Q hat naught L. That's a typical, somewhat typical scaling of normal diffusion times this log. So it has to be solved this way, and up to suppressed powers of 1 over log Q squared U. This can be solved. And in fact, this was introduced by Molière in 48, a long time ago, in the case of QED plasmas. And this is what you get. So this is the numerical, so the red band here, the red band is the exact numerical solution. And you can see 2 curves. So the dashed dotted curve, that's the Gaussian. The width of the Gaussian is given by this QS squared. That's the typical transverse momentum scale. And as you can see, it scales like L, the size of the medium, times the log of L. So there is a marginal deviation from normal diffusion due to this logarithm, the Coulomb logarithm. So this log comes from the Coulomb log. But this is necessary if we want to have a good, accurate description of the peak region. But then at high KT, we have the 1 over KT to the 4th tail, and this is accounted for by this perturbation. And then you can see by adding this orange dashed curve here, in addition to this leading Gaussian here, you get a pretty accurate description of the exact result here, as you can see. All right, so the message here is really the fact that the peak of the distribution, which describes the typical transverse momentum exchange in this diffusion process, scales like the system size times the log of L, L being the system size. So the question is, what happens at next to leading order? So a few years ago, well, almost 10 years ago, the Liu, Mueller, and Wu calculated the next to leading order correction to momentum broadening. So you see, again, this Q hat naught L, leading order 1, plus alpha bar. And they found a double log enhancement of the related.
Yacine, can I have a short question here?
Sure.
The last slide, when you have the Q, the saturation scale, that is beyond just elastic scaling, right? This is, the Q set is log linear, is L times log L. That's not within the elastic broadening picture you are just talking about, right?
This is just a result of the existence of this 1 over QT to the 4th, this Coulomb tail. So
that
so this is just the log.
I'm talking about the distance. The L is the distance you're talking about, right?
Right. Right.
Yeah. So I don't understand how come this elastic Coulomb tail can give you actual log L dependence.
Yes. So yeah. So the answer is here. So when you describe, well, if you approximate the full Mahtar equation, which accounts for this Coulomb tail, right? If you just say, well, let's use diffusion approximation, right? Then you get Q hat, and then Q hat is a diffusion coefficient. But if if the diffusion if the distribution somehow admits moments, then we should get a finite number here, right? But we don't, right? You get this UV divergence, because logarithmic divergence, which you need to cut. You could cut it at the transverse momentum KT, right? You could put KT here. You just cut it at KT instead of Qmax. And the same would happen, right? Because KT around the peak would scale as L, right? Think of it like this. Let's replace Qmax by KT. If you say Qt is much smaller than KT, that's the requirement for diffusion to be applicable, right? Qt much smaller than KT. Then I just assume that Qmax is KT, but I know that KT scales like L. I just somehow insert the KT inside the log, and I get the log of L.
Well, okay, we can probably come back this later. It really depends now how you define the Qmax, I guess.
Exactly. So this is why I went through this discussion here, because you can solve this exactly, and then you don't see these things, right? You just solve it exactly. You get this curve here. You get this curve. Now you can try to have an analytic approximation to this to the full distribution. And in doing so, you would obtain two terms. One term, the zero term, is just the standard Gaussian, except the peak position, right, would scale like L log L. So if you didn't put the log L and just assume the constant Q hat, right? If you see what I mean, if you had just a constant Q hat, you would get just Q hat L. Then you might be able to describe the peak for a given L, but if you say you look at much larger L so that the log effect would be visible, then you would see deviations. So
yeah. Okay, anyway, I don't want to drag this too long. Maybe we can probably come back. We can come back.
Yeah. So the fact that the Coulomb log somehow shows up here, it's also linked to the rest of the talk when we account for when we discuss the quantum corrections. So as I said here, the next two leading order were in the double logarithmic approximation, right? So you had soft radiation, soft gluon here radiation, and of course collinear radiation. In this limit, you get a double log. That's a standard DGLAP double log. So except the phase space would lead to this length enhancement, this length dependence. So the argument of the log is the length. I will say in the next slide why. So it's suppressed by alpha bar, but then enhanced by log squared L over 10. So of course, if the size of the medium is much larger than the mean free path, so the lower scale here would be related to the mean free path, then you could have potentially large double log, which would compensate the smallness of the coupling constant, and then you would probably need to resum those logs to all orders. So as I said, this is standard double log, but not quite. It's not quite a standard double log. So for those who are familiar with say DGLAP or BFKL, they share, of course, the same double logarithmic limit. This is almost that. In fact, it is exactly that at very high momentum transfer. That's the key. It's very high momentum transfer. It's exactly the same double log, except, which means very high, meaning looking at the asymptotic behavior of the resummed series. But here, for the moment, we are not looking at the asymptotic behavior. We're just looking at the first term here, just one radiation. And one radiation exhibit here this prefactor 1/2, and this 1/2 is very important. If you were to calculate this radiation without accounting for multiple scatterings, like suppose the problem is just linear problem like BFKL or DGLAP, and just compute this radiation here, then you wouldn't have the 1/2. You just have alpha bar log squared L. So in fact, the 1/2 comes from the fact that KT if you want to have a single scattering here, as in DGLAP or BFKL, meaning avoiding multiple scatterings, the KT transverse momentum has to be larger than the saturation scale. When KT hits, this is the region where KT goes like 1 over KT to the 4th, remember. When KT is of order QS or smaller, then you have multiple scatterings. And if you have multiple scatterings, this somehow QS acts as a cutoff here. So it cuts the infrared sector. If we didn't have QS, you would have a distribution that would rise like 1 over KT to the 4th to the infrared, to lambda QCD. But QS somehow is there to stop this growth at small KT. And this happens exactly at this saturation scale, which is Q hat tau here. And this is responsible for the 1/2 factor here. So you can write down an equation that resums those double logs to all orders. And in fact, you can show that those double logs can be interpreted and resummed into renormalization of the jet quenching parameter to all orders in the double logarithmic approximation. So Q hat here would evolve as a function of tau, tau being the formation time. So the size of the gluonic fluctuation here, the size of the gluon, which is integrated all the way to L. Okay, and then you have alpha bar, tau being again just the here this is a formation time, so it's a log, typically log of energy, or you can look at it as the log of energy or the log of there is a typo here. There should be a tau here, so it's a log of the of course of the time here, and then you integrate the transverse momentum of the gluon fluctuation up to the hard momentum of the problem, which is KT here. So this is standard, this is a double limit of BFKL or DGLAP, if you wish. The difference is again here the fact that we have a constraint on the phase space, the KT integration. You can see it here. So the phase space for this KT integration, so I have KT and tau being formation time. Again, we could use another variable, say KT and omega being the frequency. But what you see here is that you have the phase space is this rectangular area here, and the diagonal line here, this is the saturation line in analogy with saturation physics. So the double log lives in this area here, and as soon as you hit the QS, then you are in the regime of multiple scatterings and you lose the double log. This is the region where multiple scattering will damp somehow the Coulomb tail, as I just mentioned before. So
yes, can I ask a short question?
Sure.
So when you implement this cutoff from the multiple scattering considerations, so the gluons that are left are those from single collisions, and those are those predominantly like very soft gluons that doesn't change the hardness of the leading particle, so that we're still measuring the momentum broadening of the leading partons, even though we're considering there could be multiple emissions.
So the KT, you mean the KT of the KT of the gluons are still assumed to be much smaller than the energy of the leading parton, if that's your question. So
yeah, so maybe if you can go to the previous slides. Yeah, so does this KT greater than the saturation scale implies anything about the energy, the energy of the gluon?
Say it again.
Does this KT greater than the saturation scale implies any scale for the energy of the gluon?
Oh yes, sure. You can translate any constraint in KT space. So you always need, of course, to discuss the two independent variables at once, right? So here we're discussing KT and tau, right? Tau being the formation time. Now you can phrase it differently. I don't know if I can write here. Let's see if I can do that. Let's see. I probably can. So you could rewrite it like this: KT. Sorry for bad writing. I'm using my trackpad here. So okay, it's omega 2. All right. So if you somehow prefer to use the frequency, right, of the gluon, then the constraint would be KT larger than square root omega Q hat.
Okay. Yeah.
And square root omega q hat is the typical transverse momentum that would be somehow transmitted during the formation time of the gluon. And this is the typical formation time for the LPM effect, right? If kT is larger than that transverse scale, then you are in the rare event of the Coulomb tail. Exactly at this scale, this is the scale, the LPM scale. This scale is important if you study gluon radiation or energy loss. But in this problem, we need to stay away from this scale. This is the constraint.
Okay, thank you.
Okay, let's see if I can. All right. Okay, so typically, do you know how I can get rid of this? It seems to.
I think it's just use refresh.
Yeah. Okay. All right. So it's rather basic here, right? I mean, if you look at it, it's just a double log, right? It's common to BFKL, DGLAP. The only difference is this saturation line, and this saturation line is really the LPM effect. You look at it as this. It's really the LPM effect that tells you that even if you are looking at a single gluon exchange, there are multiple gluon exchanges, and you need to stay away from that. And that's the dynamical constraint. You cannot just, it's really dynamical. You need to account for each radiation needs to know where it's dynamical, because think of, for instance, color transparency. If the gluon is collinear enough, it can really go through the plasma without really interacting much with the plasma. If now the gluon explores more transverse distance, then the plasma can somehow resolve the fluctuation, and then this would lead to multiple scatterings to become more somehow important very soon. So depending on the transverse size or the transverse momentum of the irradiated gluon, you would have a different sensitivities to, it would see different number of scattering centers. So it's a dynamical statement, so to speak. So maybe a last point here is to say that this is reminiscent of the color glass condensate effective theory. So there is a saturation scale that really sets the boundary between nonlinear effects, multiple scatterings, and the linear regime of BFKL, which is BFKL. So there will be other connections with saturation. Okay, so let me maybe give a physical picture. So what changes really between going from the leading order to the next to leading order? Is it just a quantitative difference, or is there really qualitative or emergent feature that we should be looking at closely here? And there is. So I mentioned before this the leading order, the instantaneous interaction approximation, or the independent interaction approximation. So this is illustrated here by this cartoon here. So you have the gluon, the quark, the high energy quark that goes through the plasma and suffers quasi-instantaneous interactions, typically of the order of the universe to bymass. And then, of course, there's a mean free path, and then scatters again, and the mean free path. The overlapping of these two interactions is suppressed by the coupling constant. And then that's how we would get this exponentiation. And then again, especially in coordinate space, you can get an exponentiation, and then you get this semi-Gaussian distribution, and then you get this normal diffusion. Now, what happens when you resum all orders in all orders in the double logarithmic approximation plus the saturation line? Then what you get, of course, those gluon fluctuations are non-local, and they can extend all the way to the length, to the size of the system, right? Except, of course, they cannot overlap, because the overlapping, again, the saturation scale is accounting for that. So the overlap is somehow accounted for. It would be interesting to explore the overlapping formation times. I mean, there are studies there. But this goes beyond the double log approximation plus the saturation line. But if we stick to the double log plus the saturation line, then we are somehow controlling those non-local fluctuations that can extend to the size of the system. And that's quite striking, because we started with independent, quasi-instantaneous interactions at leading order, and now we are dealing with somehow fluctuations that have formation times that can extend to the length of the medium. And in this double log approximation, you can still exponentiate. if you stick again to this constraints that is given by the saturation line, this phase space constraint that I just described here. And this is the reason why we will encounter this anomalous diffusion, because now we have fluctuations that can extend all the way to the size of the system. So we have the kicks, the random kicks that the system will, that the quark will suffer, are no longer somehow local and localized. So you would have, and this would lead to system size dependence of the diffusion process. So here, as I said, tau being the size of the fluctuation is now somehow can connect the correlation length, the inverse Debye mass, to the length of the medium. All right. So maybe a connection to DGLAP here, a very quick connection. You can, now we have a description, which is double log plus saturation. Let's see what happens at very high KT. This is the hard event. Suppose you have a quark that goes through the plasma and suffers another hard event. So it's another high momentum transfer. KT is very large. Although we are still in the approximation where KT is much smaller than the energy of the quark, and so we are away from what we would think of as the x equals 1 limit, right? Which is the kinematic limit of the process. So x being the standard Feynman x. So we still have KT much smaller than the root s of the collision, but KT can be large, meaning much larger than the saturation scale. So what we are in the dilute regime. So we are in the power law region. We can expand the dipole matrix S matrix. Then you get just x per squared times q hat here. By the way, q hat can have a non-perturbative definition. We will stick here to our resummation scheme here, and then you can show that in the in a limit where you drop powers of 1 over log of KT, this just translates into this equation here, this relation here. So what do you see here? So you started with a transverse momentum, a Fourier transform of transverse coordinate space. Then you get 1 over KT to the 4th. Length enhancement, that's standard, right? Because you have one scattering, so it has to happen with equal probability along the system length. So that's L, 1 over KT to the 4th. And then you have a function, which is somehow a mild function of KT. That's just going to be a logarithmic function of KT. So it's a rough. So it's still 1 over KT to the 4th times some function of of logarithms. And this is what you get here. So at very high KT, asymptotically, you would simply get the standard double log behavior of q hat, which is exponential square root log KT squared over mu squared times log L over 0 here. And this is rather standard. This is a standard double logarithmic limit. There's an alpha s here missing. You would encounter this in any whether you look at jet multiplicity, hadron multiplicity in jets, or even in gluon PDFs. You would have just to replace the log of L by log of 1 over x, x being the standard Feynman x. But here you get, of course, this double log here. This is measured at exactly x equals to 0, what it means if you were to compute the operator definition, starting from the operator definition of the gluon distribution, you would have to put x equals to 0, and then you have to worry about how this log would appear. Okay, then of course, when KT gets even larger, close to the kinematic bound, then we would have to worry about x finite, x of order 1, and see how this would connect. We should expect an energy dependence, of course, an additional energy dependence in here, and just point you to some works where this was discussed. So this is really the large x, I would say, large KT, large x limit. And then this is the small x, but still at high KT. So it's like a transition here. It would be interesting to see how this, and it's probably just going to be given by the DGLAP evolution equation. So this is a transition between this double log to, KT of the order square root of s that would be given by DGLAP. But again, nonlinear effects due to multiple scatterings may change this picture. So this is really high KT. What happens now if we account for, we go back and say, well, we have QS, we have saturation effect, we have multiple scatterings, how this is going to change? What it means is this is still valid, this is high KT, but how high? Is it just KT larger than QS, or is it KT larger than another scale? And this is exactly the point. We will see that there is another dynamically generated scale, hard scale, much larger than QS, that will define a new window in this large KT regime, which will be still sensitive to multiple scatterings, although it is in a dilute regime. This is exactly what was also observed in saturation physics in the study of gluon saturation in DIS. So maybe a teaser here, just to kind of give you a flavor where we're going with this. So given a definition of QS that you would calculate from the solving the evolution equation for Q hat, and you plot the distribution, the transverse momentum distribution, as a function of this scaling variable, KT over QS, then you observe this so-called geometric scaling. So all of the curves for different system sizes from 10 Fermi to 500 Fermi, and then of course there's an analytic limit here that is shown here, they would roughly all go on top of each other. Right, so that's what we would refer to as geometric scaling. So this geometric scaling that you would expect to hold only around the peak region, which is the case in the leading order situation, and then of course you would see deviations at high KT. Here you see that even in high KT you still see pretty good scaling here. And the question is why? Why do you see this scaling here? So this scaling, just again, I will anticipate on that. This is really related to the fact that we are dealing here with super diffusion. This is an anomalous diffusion which exhibits scaling variance. And this scaling variance somehow extends in the region of the tail, where again, where those large steps are sampled from. So those large steps are sampled from that tail, and this tail exhibits scaling variance. So basically, even if you zoom in here, you would see the same phenomenon. There's no somehow intrinsic scaling. There's only one scaling variable here. So again, for those who are familiar with saturation physics, this is what was discussed many years ago. As some of you may know, the gluon distribution of the proton or nucleus at small x is expected to behave differently than in a dilute regime, where we would have in the Diglop evolution sector where you would, by increasing q squared, you would see more and more smaller and smaller color charges that are weakly interacting, right? So this is the Diglop evolution, where you resolve more and more charges, but with smaller and smaller sizes. If you go in the direction of decreasing x or increasing the energy, then you would have more and more gluons, which are of typical, similar size, right? Similar transverse size. And then, of course, because you cannot really accommodate as many gluons as you want inside the proton, they will start overlapping, and nonlinear effects become important. And those nonlinear effects kick in at the saturation scale here. This is the saturation line. And the description of this transition here is given by the BKG-Mork evolution equation. So there is an emergent scale, which is a saturation scale, which scales with x being Feynman x. Again, the saturation scale in this context, in the context of momentum broadening, is different. It's going to scale with a system size, while here it scales with energy. The analogy stops there. So it's really a formal analogy. There are more than just this formal analogy, of course, but these are two different physics contexts, right? Although we are computing similar diagrams, the scaling is different. It's not really the energy scaling, but it's going to be system size scaling. But there is an analogy here, as I said, as this geometric scaling. This was considered as a smoking gun for saturation physics. As you can see, it was studied, and you can see this really remarkable scaling plot where the gamma star proton cross section was plotted as a function of q squared divided by the saturation scale qs squared, and you see all of the data would go on top of each other on the same curve here, somehow exhibiting this kind of geometric scaling feature that was back then thought to be one of the signature of saturation physics. All right, so maybe I should, so I'm almost running out of time here. So let me maybe just make it less technical here. The last part of the talk is to show you that we can in fact have analytic control over this equation. We can using some mathematical analogy with reaction diffusion problems, and we can derive exact analytic results. And for instance, we can show that by assuming a scaling, right, we can find exact solution for Q hat. So we can solve this nonlinear equation and find exact solutions. X being here being the scaling variable kt over qs squared, and then we get this kind of power law distribution where this exponent beta being the slope of the kt distribution, beta being of the order of square root alpha bar. So this is Q hat here again plotted as a function of L for different values of L, and this is numerics as compared to this analytic limit here. And you see that, you know, for L equals 10 Fermi, you have the red curve, and then it starts converging slowly but surely to the analytic limit here. It doesn't. So here you see these are the deviations from this the scaling. So the scaling would be the black curve. So the scale the convergence is slow. There are some deviations. When this is for the Q hat, when of course performing the Fourier transform and looking at the transverse momentum distribution, some of those deviations somehow are washed away, but there are deviations that are there. And then QS here, from this exact solution, you can show that QS scales like L to the power 1, 1 being normal diffusion plus 2 squared alpha bar. So the deviation from normal diffusion is positive, so it's super diffusive process, and it's by summing the double logs, it's given by 2 square root alpha bar. Again, this is related to the non-locality of quantum corrections, as I tried to stress in this qualitative slide. In transverse coordinate space, it's interesting because this is also somehow connects to the physics of traveling waves. That was also studied in the context of saturation physics, but it's a wide topic in the reaction diffusion problems. So the dipole S matrix also admits traveling wave solutions, which are shown here. This is the numerical solution, again, for different sizes, system sizes. So the system size here can be seen as the time variable here, right? So you can vary the system size or just follow the particle as it goes through the plasma. That would give you the time variable. So increasing time would go from this red curve, and it goes down, it would move to the left. That's a traveling wave moving to the left. And plotting this is plotting the dipole cross-section as a function of transverse size of the dipole. Now you can use the scaling variable x per times qs, and then you see the deviations here. So you from the exact solution, the scaling solutions, and you see how this again convergence would happen here. So the question now is, are these deviations universal? So we know that the asymptotic limit is universal. So the exact asymptotic scaling solution is universal. Now the question is whether those deviations are universal. Universal meaning they are not sensitive to the initial condition. You can take any initial condition you want. Well, of course, there are restrictions to the initial condition. Let's say a broad class of initial conditions would all tend to the same curves before even reaching the scaling solution. And that's the question that is very important, because in real life, in somehow a more realistic context, the length of the medium isn't 500 Fermi. If it's 5 Fermi, 10 Fermi, are we closer to the initial condition, or can we still have? Can it exhibit some universal features even at somehow realistic system sizes? Okay, so just to again repeat myself, we can what we did is to use a technology that was developed by Brunet and Derrida to derive analytic solutions or subasymptotic solutions for the Fischer-Kolmogorov-Petrovsky-Piskunov equation, which is used for the study of population growth, wave propagations, or many systems, nonlinear systems. So this is given by this equation, which might be familiar to some of you. So you see this is just diffusion equation with a nonlinear term. Okay, so there's a nonlinear term. And this type of equations usually admit traveling wave solutions. So you would have a traveling wave that goes from the two fixed points u equals 1 to fixed point 0, they move to the right. So there's a stable fixed point and unstable fixed point. So this technology was used by Muni and Peshansky in the context of saturation physics, and in the context, specifically in the context of the Balitsky-Kovchikov equation, which is written here in momentum space. It's, if you perform a certain change of variables, then you can just map this equation to the FKPP equation, and just using the same results, formal results, they could come up with the exact solutions for the Balitsky-Kovchikov equation in the high rapidity limit, which is the asymptotic limit here. Okay, so you just using the same technology, this is what we find. Well, we find that the saturation scale, which is the typical transverse momentum exchange during the Brownian, the momentum broadening process, is given by a first term, leading term, which is a constant that is known, that can be calculated, times y being the log L over tau 0. And if you take the, again, this is written for the log, but if you take the exponential of the log, you see that QS would just scale like L to this power C. And C, I just introduced roughly here. This is C. It's 1 plus beta, roughly beta. And then there is another term, universal term, which is B log Y plus a constant. And the constant is non-universal. This form here is exactly the same form that was found in the context of saturation physics and in the context of traveling waves. Of course, the only difference would be the prefactor, which are specific to the problem we study. Even the form, the shape of the distribution for Q hat that accounts for pre-asymptotic deviations, as you can see here. So this is the asymptotic limit, exponential beta x, and then you can assume this pre-asymptotic form, which accounts for y dependence. So any additional y dependence, y being log L, would be seen as a deviation from the scaling. Scaling would be only a function of x. Additional y would be deviations. And this form here accounts for diffusion of the wavefront. And we're solving for this type of distribution, you can get exact solutions. Okay, so here's the solution. So you get again for Q hat, you get an exponential beta x, x again being log kt squared over Qs. In addition to the asymptotic terms here that I presented before, you get those pre-asymptotic terms which are also universal, meaning they don't depend on the initial condition, of course, up to 1 over y squared suppressed terms. So this is, again, the constants that we have derived here. So again, the C constant, which is roughly 1 plus 2 square root alpha bar if alpha is small, but this is the full analytic result. It's related again to the velocity of the wavefront. The slope of the wavefront is given by this beta, which is again C minus 1 over 2C. These are just analytic results. There's nothing really deep about this. But the important here maybe point is to say that this next term in the expansion here, in the asymptotic behavior of the saturation scale, this beta function is sensitive to the nonlinearities of the problem. So you get 2 over 3, 1 minus beta. And why I'm saying that? Well, you can solve this is a nonlinear problem, so it's very hard to solve, but you can make an approximation to solve it exactly. So the approximation you can make is to assume that the lower bound, the saturation scale, is not to be solved self-consistently. Just let's assume it's just plug in the leading order saturation scale, which is just proportional to tau. Of course, it's not consistent. This treatment is not consistent, but you can, hope that this effect is subleading in the double log approximation, and you can solve the problem exactly. And indeed, you get similar results. You get for QS that it scales like L to the power. In fact, there is 1 here, 1 plus 2 squared of alpha bar. That's the same result as the exact full nonlinear problem. But then the subleading term are different. So the subleading here, the term from this result that was derived by Yanko and Triantafilopoulos is 3/2. So that's an exact result, assuming a linear equation. But the nonlinear equation leads to a different prefactor, which involves 3/2 times 1/1 minus beta, beta being proportional to the square root alpha bar. So there are really leading terms, which are of the order square root alpha bar log of y, which cannot be ignored, which are somehow generated by the nonlinear dynamics. All right, so maybe trying to wrap up here. Again, I'm just flashing here the same equation, this the exact result here, pre-asymptotic result. It would be interesting to check whether this formula makes sense in practice, right? So we have solved the transverse momentum distribution here numerically. That's the, which one it is? So the numerics is the red curve here. So you see it here again, it's this red curve. Plotted as a function of kt over qs. So that's the red is the numerics, the exact numerics for L 6 Fermi alpha bar 0.2, rather somehow realistic values. Before talking about the this numerical this analytic solutions, let's first compare this the exact numerics to say the tree level. So you see the tree level is more peaked. That's the Gaussian, remember the Gaussian, and then the 1 over kt to the 4th. So it's more peaked, it drops like a Gaussian, and then it drops like 1 over kt to the 4th. And then you see the difference with the resummed is the fact that you get this widening of the distribution, simply because now we have this heavy tails, this levy tails that leads to the wider tail at high kt, which exhibit a different scaling as compared to the 1 over kt to the 4th. And then, of course, you compare the numerics to the exact asymptotic result, the asymptotic limit, which doesn't account for deviations. This is the dashed black curve, and it's not. It's okay. So it's not really. It's qualitatively. In fact, it's not doing so great, right? You see, the peak position is not really reproduced. Even the slope here is not okay. The slope. This is the asymptotic slope. Really, there's deviation here. So you could say that we haven't reached for L equals 6 Fermi. We haven't reached the asymptotic behavior yet. Still, by accounting for the subleading terms, this is the blue curve. Then we get a rather decent description of the distribution. And those terms are universal, so they are not really sensitive to the initial condition, and that's quite remarkable. So you get a distribution which is universal, and which describes which agrees with the numerical simulation for values of length of the medium which are reasonable, which somehow gives hope to use this type of distributions for phenomenology. All right, maybe go back to more conceptual conclusions.
Yacine, are you? This is the last slide.
Yes, yes,
Okay.
it's almost last. Yeah, I will be wrapping up. Yeah. Okay. So again, so we can now study the peak position, and to study it, because of course the distribution doesn't. It's a Levy-like distribution, and it will be which doesn't really admit moments, or if you were to compute the moments, they will be sensitive to the UV region. We want to be sensitive to the typical distribution, typical event. So we computed the median. So the median KT, this is again the T log T for leading order. So this is how it increases with time. So this is the typical KT increase with time. And this is the result for the typical transverse momentum, which is the QS squared, so to speak. And it's given by CT plus B log T, and it agrees pretty well with the numerics down to length of the medium of the order of 3 Fermi, which is in agreement with the previous plots, where even for rather reasonable values of L, we get a pretty good description of agreement with the numerics. All right, so let me try to wrap up here. So maybe last point is to say that there is an extension of this geometric scaling, as I started motivating in previous beginning of this section, that geometric scaling extends to much higher KTs. And the scale that really sets this is QS squared over mu, similar to that in saturation physics. So between QS and QS squared over the biomass, this is the region where you should expect geometric scaling. And in this region, the distribution has this kind of heavy tail, Levy-like tail, which is 1 over KT to the 4th minus square root alpha bar. So this is, less steep distribution as a leading order. For KT larger than QS squared over mu, we should expect to get back to the 1 over KT to the 4th. All right, this is a self-similar process, as I said. This is the fact that we have this kind of geometric scaling. So there's a scaling plus this heavy tail. This is a signature of a self-similar diffusion process, which is really a property of Levy walks, so to speak. So the distance, the typical distance, step distance is really, that is not really linked to any scale in the problem. If you zoom in, you would simply see the same process, and there's no typical scale that shows up there. So what do they have in common? All of these problems. We have transient momentum broadening, reaction diffusion problems, gluon saturation, Levy flights. Well, I mean, you have stochasticity, of course. Nonlinearity is very important. So even if you can solve the problem in the linear regime, you need to have this absorptive boundary, which is saturation scale, to get a complete description, and then the self-similarity. So this is my last slide, just to comment on the applications. So this is accounting for the resummation of double logs for momentum broadening leads to a new transverse momentum dependent distribution, which goes beyond the Gaussian approximation. So really interesting to explore this further in the context of transverse momentum dependent distributions, jet quenching, and all type of problems that I mentioned in the beginning in the introduction that relates to transverse momentum broadening. And also in the context of small x physics, we could use that initial condition in place of the MV model, which is used usually in the context of saturation physics, especially in fits to Hera. We can try to see whether this makes sense or maybe improves the fits to Hera when we use it as an initial condition for small x evolution. The third point is the search for this Rutherford scattering that was proposed by Krishna and collaborators. And clearly, because we have this heavy tail, this would enhance the probability for encountering this type of rare events. And it would be just interesting to explore this further in heavy ion collisions. And probably the exciting thing about this feature here, which is kind of emergent phenomena, is the system size dependence, momentum broadening. Can we pin down this anomalous scaling in data? And that's probably a more difficult question, as there are other somehow considerations that make this exploration more difficult. Okay, so this is the summary. Roughly, as I said, we have a super diffusive process due to large logarithmic enhanced quantum corrections. The transverse momentum broadening exhibit geometric scaling with heavy tails akin to Levy random walks. And by exploring the analogy with saturation physics and reaction diffusion processes, we can extract exact results, analytic results, asymptotic, universal asymptotic, and pre-asymptotic solutions. And the outlook is the investigation of the anomalous diffusion in heavy ion or in other contexts like in DIS and so on. Thank you. Thank you for your attention.
Well, thank you, and thank you for this excellent.
Sorry for going over time. It's
Yeah, you went a little bit over time, but that's okay. And so we can take some questions from the audience. Any more questions?
Hi, can I have another question?
Yeah, sure, go ahead, yeah.
Yeah, so when you mentioned that there is, so when you have this super diffusion, so the second moments probably it's not very well defined, so that's why you plotted the median of the
right
broadening. Okay.
Yes. Well, this is, you can see it here, right? So if you try to compute, say the first moment, kt squared, right? So you have to multiply kt squared times 1 over kt to the fourth. If you ignore the square root, if you just multiply kt to the fourth 1 over kt, kt squared 1 over kt to the fourth with a phase space, then you get the log, logarithmic integral, right? That's the log, the Coulomb log, right? And it's already divergent, right?
Yes.
Well,
Yeah.
of course, you would say, well, you have to cut it at the square root of s. But if you cut it at square root of s, this simply means that you are computing a quantity that's sensitive to rare events, to the edge of the phase space, and not the typical event, which is around the peak. And this scaling makes things even worse. So any moment compute of the distribution won't really reflect the typical event, but it will reflect really rare events that happen, in the tail.
Yeah. Also, another thing that this anomalous diffusion is so maybe counterintuitive to me is that usually if we consider like a particle shooting through a very long medium, then eventually all the momentum broadening will become like a translation invariant, right? Then which means that for every unit path length that you travel, get some momentum broadening. Then so can we like maybe tell me like how is this quantum correction can make that this anomalous diffusion to be always there, even it's like 500 Fermis in one of your simulations?
Yes, so don't take this really for face value here. When you say L 500 Fermi is really a formal limit. A lot of things will happen before you reach that scale, right? So you have to consider energy loss, many other effects. Maybe subleading corrections would become important, and so on. So really, this is just a formal limit. And you would accumulate, probably KT would become even more larger than the energy of the jet, right? So in practice you would have to put some constraints. You would have to say that KT has to be smaller than square root of s, right? Or the energy of the jet. You have to say that basically the energy loss is negligible, right? So that so this is more like a formal exercise. And if you want to somehow search for this anomalous diffusion, you would have to search for it within the realistic values of the length of the medium, and accounting for other processes there, which would somehow cloud the extraction.
Yeah. Sorry, you have a question?
Yeah, just yeah. So in electron ion collisions, so here what would be interesting, so I mean what we are probing is the gluon distributions inside the nucleus with the partron, right? So would there be any difference in the calculation if we are looking at heavy quarks, or is there a mass dependence or coming in the picture? Like would we learn anything different if we are looking at heavy quark bias instead of like inclusive like jet bias?
Right. So, well, you would have the dead cone effect, and then you would have to compare the heavy quark mass to the saturation scale. Asymptotically, any difference there would be any difference between the light flavor and heavy quarks, right? So it's going to be the same. Because you would build up, the saturation scale would be large enough so that you won't be sensitive to those differences. So as long as you are really at much higher momentum scales, then you won't be sensitive to the flavor of the particle. But of course, for smaller scales, then you might be sensitive, and that's an open question. How this dead cone effect may somehow alter this. These considerations. You are basically just introducing a new scale, new hard scale in the problem. So this would require a more, closed look.
Okay, thanks.
Okay, we should stop, but I cannot resist to ask you another question here. you mentioned already this work by Krishna and his students and Mario. So in that picture, I understand it's very intuitive. You consider multiple scattering. If you only have one single scattering, then the transverse momentum purely just power law, right? And then if you have multiple scattering, because of the random sort of random walk in transverse momentum space, you build up some kind of Gaussian form, but you still have tail at the end, and of course the transition essentially become more Gaussian as you increase the number of scatterings. And if you, my understanding is that in that picture, if you go into infinite number of scatterings, and essentially you will become a Gaussian in a sense that this peak, the transition between the Gaussian and the power law will move to very, very large K-perp. And is that what you are saying here?
So yeah, so the peak position is given by QS, which increases with system size, right? So you would have a lot, so the peak would shift to the right, right? But I think the point I want to make here, I don't know if I'm answering your question, Shia, I don't know, but so maybe this is an opportunity to make a comment. In fact, the distribution, due to quantum corrections, the distribution is no longer Gaussian here. That's the surprise. It's no longer, you cannot approximate. You can probably approximate it by Gaussian.
Yeah, you will never be a Gaussian. Somehow its transition is between Gaussian and some kind of power law, right?
Right,
of course,
exactly.
It can never be a Gaussian, yes, of course.
Right. So here, so for instance, the method I showed here this method here for the leading order, where we use this kind of decomposition, and we got this Gaussian plus a tail, right? This is an analytic approach. With quantum corrections, it doesn't work anymore. You cannot do that because the distribution, you cannot just say that you have a log which is constant.
What is your quantum correction? Your quantum correction essentially is the power law. Or...
The quantum correction change the here. So the quantum correction changed the power here. So instead of having x squared, you would have x to some power, which makes the dipole cross section to not exhibit a Gaussian behavior.
I see.
See?
Yeah,
so you have an anomaly.
That I considered this correction before, I think.
Say it again.
I don't think Krishna and the company has included such a what do you call quantum correction.
Yes, I think what they did is maybe just they did leading order, right? What they accounted in their recent paper, they accounted for maybe more kinematic constraints, the KTs of the full kinematics of the 222 process probably. So they are accounting for more refined leading order description, but not the higher orders. So the
no, I don't think so. Yeah.
Yeah.
I see. But anyway, but what do you find essentially is it will become a sort of station state. I mean, with a scaling law, I guess. The peak is sort of moving towards large K-perp as you increase the distance or number of scatterings. But if you rescale it, and that's what you find, some kind of geometrical scaling. Is that what it is? Yeah.
Exactly. So the other thing is that this is more like a formal or conceptual result. The question whether this somehow can be reached in colliders, that's a different story. For instance, maybe you see what I mean? You could maybe end up. That's why I showed this. I did this exercise here. So the exercise of looking at at reasonable values of L, and we still get the description. But still, maybe you might get away with the leading order plus a correction. And this is still maybe to be explored.
Well,
maybe
I mean,
values here, you have to be careful with the values. We're taking L6 Fermi,
Sure.
L4. There are other variables in the problem. So maybe by varying those variables, we get closer and closer to the, maybe closer to the leading order result.
Yeah. Well, even in heavy ion interaction, there are just only a few couple of scatterings, and then and we saw this in our Monte Carlo LBD simulation. You sort of like after only one or two scatterings, you develop some kind of Gaussian type of, but still with the power law tail.
Right, but this is a good point you're making here. So if you have, for certain certainty that you have at least one or two scatterings, right? You have one or two that happened, right? So let's say the average number of scatterings is above 2 or 3, right? Or of the order of 2 or 3. Then you already have, enough to kind of start building the Gaussian, as you said.
Yes. You don't need many. You only need like 2 or 3.
Right. It's a good question. Can we try to use this infinite, resummed number of scatterings and compare it to an actual global model where you really account for a finite number of scatterings, right? Or maybe just cut the distribution to a finite number of scatterings and compare it. It's probably going to do a good job, right? I mean,
that you can easily verify by just doing some kind of Monte Carlo simulation, and
right.
You can see how many number of scatterings you need to get to your analytic solution.
Right, exactly. I mean, and then of course, if you see a deviation, maybe somebody else will calculate those deviations.
Yes. Great. Okay. Well, we are really run over time, but thanks so much. We enjoy it.
Yeah, thank you very much.
Thanks so much.